Hey everyone, my name is Elric and I'm rebooting my first series where I will be creating an enterprise master data management system purely in SQL. Instead of the 30 to 120 minute videos in the first series, I will be approaching the design from an agile methodology. 10-minute videos, a Kanban board, and regular retrospectives. The master data management model will work for any business because it focuses on the needs of the data management system and the patterns of data. This system is an end-to-end system with a ton of features, and I'll explain this right after the intro, where I have a high-level keynote, basically talking about everything that we will do in this series. So, after the intro, check it out. Thank you for watching. Every piece of this system is normalized. First, normalizing the databases and their purposes. The world needs to access data, therefore we will need a database to act as a single connection to the outside world, or as I will call it, the interface database. This database will also store all of the non-system generated code. For bulk data imports, if the format of the data does not match our system's patterns, we will load it into the input database. Data in the input database will get moved to staging. The staging database is where our design patterns begin. So if the data is coming from another system like this one, or if we enable loopback features, we can skip input if we both trust the data and the data is clean. For input data and other areas of our system, we have a quality database that will use data-driven logic to test and clean data in our system. From staging, data will be moved to one of two databases: reference for rarely changing data that is not part of the business's need, and data for business's domain data, their money-making data. For example, if I was a part manufacturing company, I would store my part and people data in the data database. But maybe I want to understand what language my clients speak, and because my focus isn't on the etymology of languages, language would be considered reference data. The data and reference databases are our operating data stores. Because they are hyper-normalized in a vertical format, and we want to avoid schema changes for reporting needs, we're going to need to flatten that data out. This is where the flat database comes into play. Flat could be considered a type 1 slowly changing dimension because it's the current and flattened view of the system. From flat, the data will be moved to the warehouse for our type 2 and 3 slowly changing dimensions, into analysis for specific business intelligence inquiries, and output for data leaving the system. Data from output, if we enable loopback features, will travel back to the staging to close that loop. For the needs of the data management system, we will have a security database for parameterized access control, a planned database that will control data availability like preloading or expiring data, a display database for parameterized content, and other database for additional development information like row GUIDs or developer notes. Any row in our system can have security, display, planned, or other data attached to it. So if we store tables, procedures, web services, and business data in our system, we can be flexible enough to add any of the aforementioned functionality to any of those rows at any time. And finally, the system database. We will be spending a great deal in this series in the system database because we are building a data management system. The system database will be our information schema type database. Once we have the system building our objects, we will venture into the other databases. Additionally, the databases are actually part of a unit. A database unit consists of 4 databases: the main database type, what is considered live data, the history database type that will contain changes in the data or procedures, the archive database type for deprecated data and or procedures, and finally the snapshot database type for capturing data at a specific point in time. Pertaining to the normalization of the physical layer, we will be creating file units. A file unit is 50% of the physical layer normalization and consists of 4 files and file groups. One file space and group to hold cluster data, or the table data itself, another for non-clustered indexes, another for blob data, and finally one for columnar data. Each high-level classification will receive its own file unit. For example, a unit for reference data, a unit for people, groups, geography, and date. I'll go over how to classify data in greater detail later on in this series. Because our databases come in units, we want to make sure that when we create a file unit on a specific database, that every database in the unit has the same file unit. Moving down the line, not only are we normalizing tables, but we will also be normalizing the subjects that these tables represent. These subjects, or a table unit, consists of 4 classification tables, realm being the most general or highest level, followed by a class table that is less general than realm, a family table that is more specific than a class, a type table that is very specific considering the family, and a base table that is the most granular of the subject or unit. This table unit represents about 99% of subjects that we will need to model. There's a slight variation when it comes to dimensions like geography and date, because those are dimensional shapes, and shared attributes, which are subjects that are shared across multiple domains. These dimensions and shared attributes have slightly different base table patterns. Again, later on in the series, I will explain this in greater detail. The tables are also normalized, each containing the same 20 or so columns, a surrogate primary key, a specific dataset number, which is a table ID that essentially makes up the other half of our physical normalization, a tenant ID for multi-tenancy, a couple of sequence columns for priorities or display order, the flags for security plan, display, and the other database, descriptor columns like name, description, abbreviation, header, and a developer-only column called a key name, a classification foreign key, cleansing columns to reroute data due to deprecation or error, and active, trusted, and archived flags. These columns have the same name in every table and exist in every table. We also normalized the data types. We used user-defined data types instead of SQL data types to better define the data that we are storing. No longer will we open up a table and see nvarchar 100, we will actually open a table and see UDT name. And no longer will we have the issue where the precision is varied depending on the person who writes the code. We also normalize access to the data using views, functions, and procedures. Every table has a base view that uses a pattern involving the table name and the column name to create a system unique name, meaning we could select star from every base table using an implicit join or a comma delimited from statement and make it into a view without any ambiguous column errors. We will also be creating views for updating, inserting, deleting, and selecting. The columns available in the insert, update, delete views will vary. For example, in order to add the security to a row, it must already exist, and you wouldn't insert an archived record, so there is no need to include some of these flags in the insert view. These views will also have triggers on them to prevent data manipulation actions. You cannot delete, update, or insert to a select view. You cannot delete, update on an insert view. You cannot update or insert on a delete view, and you cannot insert and delete on an update view. The update, insert, and delete views will have procedures that are generated based on the columns they contain. These procedures will check our dataset table to see if we need to add data to the history and archive versions of the table when we perform DML action. These procedures and views help normalize the development and coding practices. And because one subject, like language, will essentially consist of, at minimum, 4 databases, 16 files, 20 tables, 100 views, 60 procedures, 80 triggers, and 400 columns, we will start this series by creating procedures that automatically generate all of these objects for us. We will be normalizing how objects are created in the system to such a degree that a single record in a base table will be all the system needs to generate the aforementioned objects. But before we get started, we need to unlearn a few things and open our minds to understand master data management better. This is object set theory, not data set theory. The primary focus is on how objects interact with each other and not joins. You will not see me use joins until we get to the flat database. Second, the first, second, third normal form, domain key normal form, we are going beyond that. Those forms talk about data, not the data management system. So this is why we are normalizing the entire process for creating objects and the physical layer and naming and everything. 3, this system is a compilation of methodologies and techniques, and it's never or. It's not Inman or Kimball. 4, instead of just a type table, we will always work in 4 degrees of abstraction. 5, the system focuses on vertical storage instead of schema changes, so this increases real-time expansion by reducing object change deployments. And finally, we need to prepare ourselves mentally to visualize code paths, because we will be using tables to drive our logic instead of code. For example, we will be creating a decision engine that can compare and calculate anything with anything in our system, and we will expand that by rows in a table and not more code. So this type of abstract thinking is a must. So grab a copy of SQL 2017 or later, and let's get started. I will see you in the next video.